Hi, and welcome to this important video on Newton's laws of motion. This is a topic that a lot of students find tricky, but hopefully by the end of this video you won't be one of them. Most textbooks kick this topic off with pretty scary looking statements of Newton's 3 laws of motion, which look something like this. Daunting as they might seem, you should do your best to learn all 3 laws off by heart and to know which is which. Doing so will make your life a lot easier in the long run, plus your examiner's gonna think you're a complete physics legend if you can mention the first, second and third laws of motion in the right places in your written answers. Let's take a closer look now at each law. Newton's first law states that if the resultant, or the unbalanced force acting on an object, is 0, then its acceleration will be 0 too. What this means is that if the object is at rest, it'll remain at rest, but if it's moving, it'll continue to move with constant velocity. Remember that just means it'll have a constant speed and its direction of motion won't change. Have a look at this box as it sits at rest on the ground. Its weight, which is acting downwards, is balanced by the upwards normal reaction force from the ground, so the unbalanced or resultant force acting on the box is 0. Because the box is already at rest, it will remain at rest. Exactly the same thing happens to the box when these two men try and push it in opposite directions with equal forces. Because the resultant force acting on the box is still 0, it will still remain at rest. Remember though that Newton's first law also applies to objects which are moving with constant velocity. If you're ice skating and the only 2 forces acting on you are your weight and the normal reaction force, then you'll continue to move with constant velocity until an unbalanced force causes you to accelerate or decelerate. In practice though, there's always going to be a small amount of air resistance or friction acting on you, which means that you will decelerate to rest eventually, as long as you don't hit something first, of course. Likewise, if our unlucky astronaut is stranded and is moving with constant velocity in deep space, then they'll continue to do so as there's no resultant force acting on them. As a matter of fact, there are no forces acting on them at all. Moving on, Newton's second law says that an object will accelerate if there's a resultant force acting on it. The acceleration of the object is proportional to the resultant force acting on it, and inversely proportional to its mass. No doubt you're delighted to hear that there's an equation to go with Newton's second law, and it looks like this: F equals ma. F here stands for the resultant, or the unbalanced force acting on the object, which is measured in newtons. M is the mass of the object in kilograms, and A is its acceleration in meters per second squared. If we make A the subject of this equation, we can see that A is equal to F divided by M, and it's by doing this that we can see that the acceleration of an object is proportional to the resultant force acting on it and is inversely proportional to the mass of the object. In other words, larger resultant forces mean larger accelerations, but larger masses mean smaller accelerations. Have a look at this first example of using F equals ma now. As you can see, the boy's mass is 50 kilograms and his acceleration is 1.2 meters per second squared. This is a nice straightforward substitution question, so starting off with F equals ma for our resultant force, that becomes 50 times 1.2 to give an answer of 60 newtons. On to example 2 next. Starting off by highlighting our key terms, the mass of the car is 1500 kilograms and there are 2 forces acting on it. The first, the driving force, acts in the forwards direction and the resistive forces act in the opposite direction. What we're going to do here is to draw in the forwards force acting in the car, which is 6 kilonewtons, and then the backwards force next, which is 2 kilonewtons. So we can see that the resultant force acting is just 4 kilonewtons, or 4,000 newtons. Then rearranging F equals ma, A equals F divided by M, which is 4,000 divided by 1500, to give a final answer of 2.7 meters per second squared. Have a look at example 3 now, where a lorry of mass 5,000 kilograms is accelerating at 1.5 meters per second squared. Part A is nice and straightforward. We're again just using F equals ma, then subbing in, that becomes 5,000 times 1.5 to give an answer of 7,500 newtons or 7.5 kilonewtons. Part B is quite a lot trickier. As you can see, we need to work out the frictional force between each of the lorry's tyres and the road. We know that the resultant force acting to the right here is 7.5 kilonewtons. That means that the driving force minus air resistance minus the total friction must be equal to 7.5. So if we sub in our numbers here, that becomes 11 minus 2 from the diagram minus the total friction must be equal to 7.5, which means that the total frictional force acting between the tyres and the road is 1.5 kilonewtons. Because the lorry has 4 tyres though, we have to divide this number by 4 to give a final answer of 0.375 kilonewtons, which is 375 newtons. We're going to take a quick break now to look at one of the higher tier topics, inertia. Have a look at these two diagrams. Which vehicle will be easier to push? The car, of course, but why? We know that Newton's first law tells us that if the resultant force acting on an object is 0, then its acceleration will be 0. The tendency of an object to remain at rest or at constant velocity is called inertia. It's for this reason that Newton's first law is often called the law of inertia. Get ready now for the hard part. Here it is. The greater the inertial mass of an object, the more difficult it is to change its velocity. So what does that actually mean? Believe it or not, you know already, and it's explained by the equation F equals ma. The correct name for m here is the inertial mass of the object. So if we rearrange our equation, it becomes A equals F divided by m, resultant force divided by mass. In other words, for a given resultant force acting on an object, if its inertial mass is bigger, then its acceleration will be lower. That's why it's more difficult for the man here to push the lorry than it is for him to push the car. On to the last of Newton's laws of motion now. Newton's third law says that when one object exerts a force on another, the second object will exert an equal and opposite force on the first. Both forces must be of the same type. Let's look at a few examples. If you exert a force on a wall, like this, then the wall will exert an equal and opposite force on you. You push the wall and the wall pushes you back. Both forces are contact forces here. Moving on. When we get into a car or bus and it just magically moves forwards, we don't often think about how. Because of the friction between the tyres and the ground, when the wheel rotates, the tyre exerts a force on the ground. This causes the ground to exert an equal and opposite force on the tyre, and the vehicle moves forwards. You might be interested to know that friction explains how we can walk in exactly the same way. We push back on the ground, and by Newton's third law, the ground pushes us forwards in return. Newton's third law also applies to non-contact forces like electrostatic forces. Here, for example, because the positive charge is attracted to the negative charge will be attracted to the positive one in return. Looking at gravity now, we know that there will be a gravitational force acting between all objects with mass, and so because the Earth exerts an attractive force on the Moon will exert an equal and opposite attractive force on the Earth. Just one last point now on Newton's third law in case it does happen to come up in the exam. Remember that both forces must be of the same type. Let's look at our ice skater again for just a moment. If she's balancing at rest as shown, then the only two forces acting on her will be her weight and the support or normal reaction force from the ground. Do these forces form what we call a Newton's third law pair? A lot of people would say yes here, and it's easy to see why, because both forces are equal in size and opposite in direction, but they actually don't form a pair in this way. The reason for this is that both forces are of different types here. The support force is a contact force, and her weight is a non-contact force, so they can't be paired in this way. Remember that what we call her weight is actually the gravitational force exerted on her by the Earth. Its reaction force will be the gravitational force which she exerts on the Earth in return. The support force acting on her is exerted by the ice, so its Newton's third law partner will be the equal and opposite force which she exerts on the ice. That's plenty on Newton's third law, so let's just finish off with a brief recap of his first and second laws. The key equation for this part of the course is F equals ma. Just remember that F stands for the resultant force which is acting on an object. Newton's second law says that the acceleration of the object is proportional to the resultant force acting on it, but is inversely proportional to the object's mass. We saw that Newton's first law is also called the law of inertia. We can actually remember it as a special case of Newton's second law. If F equals 0, then we can rearrange F equals ma to show that the acceleration of the object will be 0. In other words, if the object is at rest, then it will stay at rest, but if it's moving with constant velocity, it will stay moving with constant velocity. In the required practical for this topic, you have to investigate the factors that affect the acceleration of an object. More specifically, you have to look at how the acceleration of an object is affected by the resultant force which is acting on it, and its mass. If that's gone straight over your head, this table should help clear things up. We can use pretty much the same experimental setup for each of these investigations. As you can see, the masses which are attached to the end of this piece of string provide the force which accelerates the trolley. For the first part of this investigation, we vary the force which is applied to the object, the trolley, by changing the number of masses which are attached to the end of the string. For example, if the mass attached here is 300 grams, that's 0.3 kilograms, then the accelerating force is just given by the weight of these masses, which is given by W equals mg, the mass times the gravitational field strength, then subbing in, that becomes 0.3 times 9.8 to give an accelerating force of 2.94 newtons. Determining the acceleration of the trolley for each applied force requires a little more thought, and that's where the light gate comes in. A light gate can be set so as to measure the velocity of something which travels through it. How it does this is by measuring the amount of time which the object takes to pass through it. When the piece of card which is attached to the top of the trolley, the flag as it's called, first cuts through the beam of the light gate, an electronic timer is started automatically. As soon as the flag leaves the light gate and the beam is no longer blocked, the timer is stopped. If we know the length of the flag which is attached to the object, then we can work out its average velocity in the light gate by using this equation. Average velocity equals length of flag divided by time taken. In practice, this is all done automatically by the light gate and the data logger which it's connected to. As the experimenter, you just have to program in the length of the flag. Moving on, if we know the velocity at which the object is travelling through the light gate, then working out its acceleration is fairly straightforward. If we release the trolley here from rest, so that its initial speed is 0, then time how long it takes to get to the light gate using a stop clock or stopwatch. Its acceleration can be calculated using the equation acceleration equals change in velocity divided by time taken, or v minus u divided by t. Because we've released the trolley from rest, u equals 0 here, so this equation simplifies to a equals v over t, the velocity of the trolley at the light gate divided by the time it took to get there. In practice, we might repeat and average our measurements to make the results more accurate. This isn't the only way in which this experiment can be carried out. If you have two light gates connected to a data logger, you can measure the acceleration of the trolley directly. With this setup, the data logger measures the velocities of the trolley at each light gate, u and v, and the time it takes for the trolley to travel between them, before again using a equals v minus u over t, the change in velocity divided by the time taken, to work out the acceleration of the trolley. Results obtained from this investigation might look something like this, and a plot of the acceleration of the trolley against the resultant force applied to it like this. A best fit line through these points should be a straight line through the origin, which means that the acceleration is proportional to the resultant force. Doubling the force doubles the acceleration, and so on. Now that we know Newton's second law, we can actually work out the mass of the trolley from our best fit line. Rearranging F equals ma, where F is the resultant force in the trolley, we see that its mass is given by m equals F over a. So taking any two values of F and a from the best fit line, such as these ones, we can see that the mass of the trolley in this investigation was roughly equal to 1 kilogram. In the second part of this investigation, we change the mass of the trolley, keeping the force constant. The results you might obtain here might look something like this. As you can see, As the mass of the trolley is increased, its acceleration decreases. A graph of these results looks like this. Again, from Newton's second law, we can see that A equals F over m. In other words, the acceleration of an object is inversely proportional to its inertial mass. Doubling the mass of the object causes its acceleration to half, trebling its mass causes its acceleration to fall by a factor of 3, and so on. One of the control variables in this investigation is the accelerating force. Can you think of any others? That brings us to the end of this video on Newton's laws of motion. Have a go at the exam style questions and good luck!